The reaction quotient is symbolized by the capital letter Q, and it tells us whether a reaction is at equilibrium or not. If the reaction is not at equilibrium, it also allows us to predict which direction the net reaction will go to reach equilibrium. For example, let's look at the hypothetical reaction where gas A turns into gas B. Gas A will be represented by red circles or red spheres, and gas B will be represented by blue spheres. The equilibrium constant for this hypothetical reaction is equal to 3 at 25 degrees Celsius. Let's start by writing out the expression for the reaction quotient. So we would write out here QC is equal to, and this has the same form as the equilibrium constant expression. So we would put concentration of B to the first power divided by the concentration of A, also to the first power. Let's look at our first particulate diagram here, and let's think about each particle representing 0.1 moles of a substance, and the volume of the container is 1 liter. So let's first find the concentration of B so we can plug it into our expression for Q. B are the blue spheres, so we count up 1, 2, 3 blue spheres. Each sphere or each particle represents 0.1 moles, so 3 times 0.1 is 0.3. And then we divide that by the volume of 1 liter to get a concentration of 0.3 molar. So we can go ahead and plug in 0.3 molar for the concentration of B. Next, we divide that by the concentration of A, and since there are 5 red particles, and each particle represents 0.1 moles, 5 times 0.1 is 0.5 moles of A, divided by a volume of 1 liter gives a concentration of 0.5 molar for A. Notice that we could have just counted the number of particles, 3 blues and 5 reds, and just done 3 divided by 5, and get the same value for the reaction quotient Q. So QC is equal to 3/5 or 0.6, and KC, remember, was equal to 3. So Q is not equal to K. In this case, QC is less than KC. Since Q is not equal to K, at this moment in time, the reaction is not at equilibrium. In order for this reaction to reach equilibrium, Q needs to be equal to K. And since Q is a lot smaller than K, if you think about it, we need to increase the numerator and decrease the denominator. So that means we have too many reactants and not enough products. And so the net reaction, if we go back up here to the equation here, the net reaction is going to move to the right to make more products. So the net reaction moves to the right to make more blue particles, and therefore the number of red particles would decrease. We can see that comparing these first 2 particulate diagrams here. So let's compare the first particulate diagram to the second particulate diagram. In the first particulate diagram, we had 3 blues and 5 reds. And the second particulate diagram, we have 5 blues and only 3 reds. So that shows the reaction has moved to the right to increase the amount of products and to decrease the amount of reactants. Let's calculate QC at this moment in time for our second particulate diagram to see if we've reached equilibrium yet. Well, we have 5 blue particles and only 3 reds, so QC would be equal to 5/3 or 5/3. Remember that the equilibrium constant Kc is equal to 3. Therefore, QC is still not equal to Kc, and therefore the reaction is not at equilibrium. And Q is actually still less than K. Therefore, the net reaction is going to move to the right again to increase the amount of products and to decrease the amount of reactants. Let's compare our second particulate diagram to our third particulate diagram. In the second particulate diagram, we had 5 blues and 3 reds. And in the third one here, we have 1, 2, 3, 4, 5, 6 blues and 2 reds. So we've increased in the amount of blue and we've decreased in the amount of red. Let's calculate QC for the moment of time represented by our third particulate diagram. Well, there are 6 blues and only 2 reds, so QC is equal to 6 divided by 2, which is equal to 3. So QC is equal to 3, and remember K is also equal to 3, so QC is equal to KC, and therefore this reaction is now at equilibrium. And at equilibrium, the reactants turn into the products at the same rate the products turn back into the reactants. And therefore, the concentration of both reactants and products remain constant at equilibrium. So when Q is less than K, the reaction is not at equilibrium. There are too many reactants and not enough products. Therefore, the net reaction goes to the right to increase the amount of products. The net reaction continues to go to the right until Q is equal to K and the reaction has reached equilibrium. At that point, the concentrations of reactants and products stop changing and they remain constant. It's also possible for Q to be greater than K, and if that's true, the reaction is not at equilibrium, but in this case, you have too many products and not enough reactants. Therefore, the net reaction goes to the left to increase the amount of reactants and to decrease the amount of products. The net reaction will continue to go to the left until Q is equal to K and the reaction reaches equilibrium. Let's look at another reaction, which is the decomposition of phosgene to form carbon monoxide and chlorine gas. Kc for this reaction is equal to 2.2 times 10 to the negative 10th at 100 degrees Celsius. And let's say we're given concentrations of phosgene, carbon monoxide, and chlorine at a moment in time and asked if the reaction is at equilibrium or not. And if the reaction is not at equilibrium, we need to predict which direction the net reaction will go to reach equilibrium. Our approach is going to be to calculate QC at that moment in time and then compare QC to KC. So first we need to write our QC expression, and this is equal to the concentration of carbon monoxide raised to the first power times the concentration of chlorine raised to the first power. And that's divided by the concentration of phosgene, so the concentration of COCl2. So at this moment of time, the concentration of carbon monoxide is 3.4 times 10 to the negative 6 molar, the concentration of chlorine is 6.0 times 10 to the negative 6 molar, and the concentration of phosgene is equal to 2.0 times 10 to the negative 3rd molar. When we plug all those into our Q expression and solve, we get that QC is equal to 1.0 times 10 to the negative 8th. So in this case, QC is greater than Kc because Qc is equal to 1.0 times 10 to the negative 8th and Kc is equal to 2.2 times 10 to the negative 10th. And when Qc is greater than Kc, we have too many products and not enough reactants. Therefore, the net reaction is going to go to the left, and there's going to be an increase in the amount of phosgene. The reaction will continue to go to the left until Q is equal to K and the reaction reaches equilibrium.